So the applause is premature, of course. You don't. So, I begin by saying happy birthday to Russ, and I'll begin with a very brief remark about why I think it's appropriate. I mean, some of you have already heard me explain this at other 60th birthday meetings, but in any event, happy birthday, Russ. And now I will briefly explain to those who don't know why a 60th birthday celebration is especially important. According to the Bible, you can see this in Leviticus, in the end of Leviticus chapter 27. The Bible gives numerical values to people's worth. When a person promises to bring to the temple his value, so he makes a promise, my value is going to be given to the temple, the Bible specifies what the value of a typical person is. And it turns out that until the age of 60, adult men, their value is 50 shkalim. These are not the shkalim that pass for now, but these were real shkalim that weighed whatever. And at the age of 60, from 60 and up, his value drops to 15. Now, a person feels, my worth has gone down so much. What is going on? And so people gather to encourage him and tell him that perhaps his monetary value for the temple has gone down, but his value to the mathematical community, I'm sure, has not and will continue to increase over the years. So happy birthday, Russ.
You are a counter-example to the Bible. This is a double special measure. You personally.
Oh, no. Gil, stop. No. Okay. So, perhaps some of you don't know, but Russ started out his mathematical life not as a probabilist, but as a harmonic analyst. And when he came as a postdoc to Stanford, he came because there was a tradition of harmonic analysis at Stanford. Izzy Katznelson was there, and somehow or other, some of the people at Stanford who were interested in ergodic theory, and some of the sort of permanent visitors there, like Hillel, got him interested in problems in ergodic theory. And Russ made the first serious progress on one of Hillel's famous problems, the times 2 times 3, which I'm not going to discuss at all. And instead, I'm going to tell you a brief story about some connections between harmonic analysis and probability theory. So, I don't have to explain here. Yes. I do have to find something that writes. I don't have to explain here what is a stochastic process. So this is a stationary stochastic process. And we'll always assume that the expected value is 0, and for the purposes of this talk, we will always assume that there is a finite second moment. And then there's a harmonic analysis invariant connected to this process. It's called the spectral measure. The spectral measure. And last week, Russ and I were both, Yuval as well, were at a workshop, and Russ was giving a series of talks, and he spent maybe 10 or 15 minutes explaining the spectral theorem to the audience, thinking that they may not know what it is. For probabilists, he explained the spectral measure, the spectral theorem, in the functional analytics way, for probabilists, you get to the spectral measure in the following fashion. For a stationary process, you can define the covariance function, which is the expected value of x0 with xn. We'll always be talking about real valued, although actually that's not so necessary. Cn is the covariance function, and Cn is a positive definite sequence. And therefore, Cn is the Fourier transform. Well, just have to need 0, 2 pi e to the minus 0, 1, e to the minus 2 pi I n d mu theta, where d mu is a probability measure. Yeah, that's when this is normalized so that the is a probability measure on the unit circle. This fact predates the spectral theorem. It's a theorem of Herglotz from the early 20th century. And this associates to a stationary stochastic process a measure called the spectral measure. Now, the story I want to tell you begins with a talk that Misha Sodin, who was here, Misha Sodin gave in Jerusalem, in which he explained a new theorem that he and his collaborators, so Borichev and Misha Sodin, found as a byproduct of their investigation on some properties of entire functions. They found the following interesting fact about real-valued stationary processes. So this is their theorem. If xn is a finite-valued stationary and just ergodic, I will always assume my processes are ergodic, although that's not strictly necessary. Finite value stationary ergodic process, then either xn is periodic or the support of the spectral measure is equal to the whole circle. So in general, of course, there's no reason for the support of the spectral measure to be the whole circle. He actually wrote and asked me if I knew of such a theorem, and I didn't. And it seems somewhat surprising that this kind of hypothesis leads to such a dichotomy. Now, their proof of this relied ultimately on a theorem of Zagar. Perhaps you'll correct me if how I should be pronouncing this name. How should I be pronouncing this name? Miklos. Zagar. Zagar. Okay. The theorem of Zagar, which concerns functions, power series. So if the AN take values in a finite set either, so here is a function. If the an take values in a finite set, then clearly the radius of convergence is 1. Then either f is rational or the unit circle is a natural boundary. So this was a result of Zegers. Actually, I think the problem goes back, this is from the 20s of the last century, the problem goes back to Polya, and the first result on this problem was by Hausdorff. This is a result which is less well known. Hausdorff showed, well, okay, I'm supposed to end at what time? Let me know, and so I can plan how much and what I should be saying.
So
10:20. Okay. Okay, so maybe I'll come back and tell you about Hausdorff. In any event, I was very struck by this problem, by this result. And it's been several years that I'm retired, but I still volunteer and I teach. And that spring, I was teaching a course in real analysis, some graduate course in real analysis. And on that occasion, I was preparing for one of the topics, and I had a look again at an old book in harmonic analysis by Henry Helson. And in Helson's book on harmonic analysis, I found another theorem which Helson called Zegers Theorem, although he does point out that Zegers didn't quite prove this theorem, but in a problem he gives this result of Zegers. But what he calls Zegers Theorem in his book is the following. So I call this Helson's theorem, although, what? Yeah. So if an is a sequence with all of the ANs belonging to some finite set, finite subset, say the complex plane, then either AN is periodic or the spectral set of AN is T. Now, what is the spectral set of a bounded function? I will explain to you in a moment. But I was struck by the fact that with this theorem, we can get information about the spectral set of a sample point of this process. So the only thing that was left was to relate the spectral set of a sample point to the spectral measure of the process. So then I asked some of my friends whether they knew of such a result, and none of my friends knew of such a result. And so what I finally wound up doing was proving the following theorem. So if xn is a bounded ergodic process. Again, I always normalize so that xn, yes, bounded ergodic stationary. Xn is 0, then the spectral set of almost every sample point coincides with the support of the spectral measure of the process. Now, I still owe you an explanation of what is the spectral set of a bounded sequence. Before I give it, I should point out that whereas this theorem is about finite value, these are stationary stochastic processes indexed by the integers, this theorem is valid, so the above, so maybe I'll give it a name, 1, the above theorem 1 holds for all locally compact abelian groups. Yeah. So, do I still need to keep this on the board?
Can you erase that?
I can erase it. Okay. So now, what is the spectral set of a sequence? So this was defined by Björling, Björling. Probably the original definition was for R, bounded functions. For locally compact abelian groups, the definition is probably due to Cartan and Goldmont. And this can be defined in several ways. So definition spectral set of AN is so here are several definitions. Is the support, the closed support of the Fourier transform of AN. Maybe I put this in quotes. For this definition, you have to know what is the Fourier transform of a bounded sequence. Now, ordinarily, for the Fourier transform, for a Fourier series, you want to sum, you want to do something like this. And if AN is in little L1, then this just converges. If it's in L2, this defines an L2 function. If it's just a bounded sequence, I mean, it's a little more difficult to make sense of this, but you can make sense of it in terms of distributions, and then it's the closed support of the distribution. Here's a more concrete way of describing it. You look at the closed you look at the closure of the translates of AN. So a translate of AN is the shifted sequence. You look at the closure of the translates in the weak topology coming from little L1 of Z. So the dual space of little L1 of Z is the space of bounded sequences. It's L infinity, and there's a weak topology on L infinity coming from this dual space. You look at the closure of the translates, then the spectral set consists of those exponentials spectral set lambda consists of all those exponentials which you can find in the weak closure of the translates of the sequence. And by duality, it's easy to express this as the support of those functions which L1 functions which annihilate the sequence, which I will not describe at the moment. In any event, this is a set which can be defined just in terms of the sample sequence. Now, of course, if you know a typical sample sequence, you can compute the covariance function and then take its Fourier transform, get the spectral measure, and find its support. But this spectral set is something which is directly associated with a single sample, and what the theorem tells you is that this spectral set coincides with the support of the measure. Now, we don't really have time for me to explain the proof of these theorems. I also wanted to tell you about another theorem or two which connects finite valued stationary processes with their where in the statement you don't see harmonic analysis, but harmonic analysis appears in the proof of the theorem. This is an older result of mine from about 10 years ago, and it has with it an open problem, so let me maybe begin with...
Is this a measure on the spectral set?
No. No, it's the support. It's a closed support of the... No, there's no... I mean, not that I'm aware of. Perhaps somebody here can correct me, but I don't know of any natural measure. Okay. So now I will tell you another story. The common thread between the two stories is finite valued stationary stochastic processes and harmonic analysis.
Can I make one quick question? So is it the immediate correlate that the spectral set only depends on the covariance structure of the...
No.
But
I mean, of course, it's a consequence. It depends only on the covariance function. Of course. Yeah.
But that would not have been obvious a priori.
I mean, what is obvious or not, I don't know. I mean, it's as I say, I don't think probabilists, most probabilists, unless they've been educated in harmonic analysis, don't really encounter Björling's spectral set, I think. I mean, I'm not aware of its appearance. I mean, although there are many probabilists here, and you can correct me if you have other applications of it, but I'm not aware of too too many papers in probability theory where Berling's spectral set appears. I mean, Yuval probably could tell me if...
I've seen it, but not in a probabilistic context.
Okay. No, I mean, I'm sure you've seen it, but you certainly read Izzy's book, and it's there. So it's okay. So this other story concerns entropy, which I'm not going to define. So let me begin with, again, a finite valued stationary ergodic process. And what I want to study now is what I call a linear factor. Linear factor. And the first definition I give depends on an L1 function. So let Cn be an L1 function. So this is real or complex valued and finite, and we now have an L1 function, and we define Yn as the sum of Cn minus k xk. Yes?
Over here, you take the linear span somewhere?
No.
So,
No, I do not want to take a linear span.
so how are you going to get things of absolute value 1 if an, for example, never has absolute value 1?
The closure of the translates. Wait, do I? No, I take the linear span. I'm sorry. Yeah. Sure. Topology. Yeah. Closure, linear span. Linear closure. Yeah, we're going to use duality. You use duality to connect this with the set where the certain class of L1 functions vanish. You look at the L1 functions which annihilate it, and you look at their where they vanish. And that, if you yeah, the dual statement is you look at those L1 functions C such that C star of A vanish identically, and then the Fourier transform here would be the product, and on the set where this vanishes, if the support of A hat is in that set, then this will be 0. So you look at the common zeros of the L1 functions which annihilate A. And that gives you a linear space. And so you need the linear span. You're right, I'm sorry. I should have said that. So here again we have a convolution. When I have an L1 function, I have a bounded function, I get a new stochastic process. So the theorem now states the following. If C is not identically 0, then the entropy of Yn, this is maybe I should use little h. So this is the Shannon entropy. So this is the average entropy. This is the limit of the entropy of Y1 to Yn divided by n. This is the usual Shannon entropy. Then h of Yn equals h of xn. So if you take a linear factor, if it's not 0, then you don't lose any entropy. The way I proved this originally was using a theorem of D.J. Newman, which concerned the translates of little L1 functions, translates of elements, such that Cn equals 0 for n less than 0. So these are what correspond to analytic functions, and the closure of the translates here has support on functions here have support on the whole unit circle, and using this theorem and some notions of conditional entropy, I proved this. What is interesting here is that there's another sense in which one can take a linear factor. So again, xn, a finite valued stationary ergodic process, but now look at L2 of, this means the linear span closed linear span of the xn's in L2 of the probability space. And now you take some y, 0, which is an element here, and this defines a process. You take a finite valued, say, or bounded, it doesn't matter. You take this process and you can ask for the entropy, finite or bounded function here, and ask for the entropy of the yn process. You can ask for the entropy of this process even if it's real valued in the sense of ergodic theory. This defines the way I want to think of this is that you look at the smallest sigma algebra that is generated by the YNs, and then you look at the entropy here. So this is an L2 version of linear factors, and now the theorem is different. Now the theorem is either the entropy of the Yn process equals the entropy of the original process, or, and this can happen, it equals 0. So you can't get an intermediate value, but you can get the value 0. This can happen in this L2 sense. It can't happen in the L1, in the L1 version. There's a difference between L1 linear factors and L2 linear factors. Yeah. A quick example for this kind of phenomenon is the following. You can start with xn, say, or xn IID, and then take another, say, Zn, which comes from an irrational rotation and you look at the product of these. So you look at the product. Now this product space looks like this. Here's where you see the IID, this some measure space here, and here's where you see the circle. Now, if you take a partition like this of the circle into two sets, you'll get something that has zero entropy. Now, you can perturb it a little bit. So perturb the partition.
Are they coin flips? I didn't hear what the IIDs were.
IID, make them coin flips. IID plus minus 1 with probability a half. The simplest positive entropy process that you know. And now you perturb this partition a little bit so that it's not measurable with respect to the irrational rotation. It has some IID factor, but it's not far from the irrational rotation. And you get a process, and this process has to have in it this irrational rotation as a factor. And so you can, in the L2, that will have a non-trivial projection onto the circle. So such a maybe I shouldn't have called these xn's, but anyway, now I have ZWN. This is defined by here it's 0 and here it's 1. The WN process has a non-trivial projection.
Red is not very visible.
Excuse me?
The color is not very visible.
The color is not visible. Here's a perturbation. There's WN. You get a non-trivial projection onto the irrational rotation. And that gives you this non-trivial projection will give you a zero entropy factor in the L2 span of these variables. So this is what can go wrong, and except for that, you can check that nothing goes wrong. In other words, modulo the Pinsker factor, you're going to get, again, recover the whole process. Now, the last thing I want to do is explain to you how I came upon this strange theorem that the entropy doesn't drop, because there's a problem which is still open. I don't think it's attracted much attention, but I'll now popularize it again. So, problem. Let xn be an IID process with xn taking the values, say, in 0, 1, with a continuous distribution. So all I want to assume about this distribution is that it's a continuous distribution. An example would be the Lebesgue measure, but you could have any continuous distribution on the unit interval. And now let...
Continuous
Continuous means absolutely continuous?
No. Continuous means atomless. This is the measure theory. I mean, I think in measure theory you say continuous distribution. What I mean literally is that the distribution function, f, the distribution function of this variable, I mean, f of t is the probability that xn is greater than or equal to t. I mean that this is a continuous function. I mean, in old books on probability theory, there were no sample spaces. There were bold-face random variables, and there were distribution functions, and that's it. So there was no measure theory. It was xn be an IID process with xn with an atomless continuous distribution, and Cn not identically 0 in little L1 of z, and you define Yn to be this process. Xk. So this is what's called sometimes in statistics moving averages. I'm doing it two-sided, but moving average, you have IID and you have some linear function of this. Problem. Prove that the entropy of this process is equal to plus infinity. So, of course, a continuous IID process has infinite entropy. You can refine it and get as much entropy as you like, and so the entropy is infinite. You take an...
What are the CIs?
The Cn is a sequence. It's an element in little L1 of z, so these are just real valued,
An arbitrary sequence.
an arbitrary sequence which is not identically 0. No. I have don't care about. What?
So Yn is a new process.
Yn is a new process which is defined by this formula. It's the moving average of this IID process. It's a new process. It's not identically 0 because I've assumed that this Cn is not identically 0. I don't want a triviality. And all I ask you to prove is that this has infinite entropy.
And you expect something even stronger?
No. I mean, what is stronger than infinity? I mean, in a topological setting, if I were talking about the mean dimension, I would maybe want to expect something stronger, but I'm not. And so I don't want to get into the topic of mean dimension and of topological dynamics. So I don't know of anything stronger than this. And I will say that in the paper, which appeared about 10 years ago, that I wrote on these linear factors, I prove this when the distribution is uniform, is Lebesgue. And I prove it for the Lebesgue measure, for example, using this fact, that finite entropy factors, the entropy you lose no entropy. So I used this as a tool to prove this for some special distributions.
That's when X is Lebesgue?
When the distribution, when the xn is Lebesgue. Yeah. When the xn is Lebesgue, I can represent it as a sum of discrete variables which are independent. I mean, it is itself, this is a convolution, an infinite convolution of finite measures. So whenever this is a convolution of finite measures, you can use the theorem that I wrote there in order to deduce this. But the general case I don't know how to do. I haven't known for a long time, and I leave it for you as a problem. Thank you.